Hello, my name is Hashim, I'm FIC.
Hello, my name is Vincent. I'm from FIC.
Today we'll be doing question number one.
Table 1 lists the average carbon dioxide level in the atmosphere, measured in parts per million at Mauna Loa Observatory from 1972 to 1990. Use the data in Table 1 to find out a model for the carbon dioxide level.
Estimate the average CO2 level for 1987 and to predict the level for the year 2005. According to this model, when will the CO2 level exceed 400 parts per million?
Okay, to solve question number 1, here are all the workings. For the first step, we need to find out how do we calculate the slope and the intercept. To calculate the slope, we need to use n sigma xy minus by sigma x sigma y divided by n sigma x to the power of 2 minus x sigma x squared. For find intercept, we need to use sigma y minus n sigma x divided by n. So sigma x equals to 2 plus 4 plus 6 plus 8 plus 10 plus 12 plus 14 plus 16 plus 18 plus 20 equals to 110. For sigma y equals to 327.3 plus 330.0 plus 332.0 plus 335.3 plus 338.5 plus 341.0 plus 343.3 plus 347.0 plus 351.3 plus 354.0 equals to 3400.3. To find sigma xy equals to 2 times 327.3 plus 4 times 330.0 plus 6 times 332.0 plus 8 times 335.3 plus 10 times 338.5 plus 12 times 341.0 plus 14 times 334.3 plus 16 times 337.0 plus 18 times 351.3 plus 20 times 354.0 equals to 37,901.6. To find sigma x squared equals to 2 squared plus 4 squared plus 6 squared plus 8 squared plus 10 squared plus 12 squared plus 14 squared plus 16 squared plus 18 squared plus 20 squared equals to 1,540. Now to find slope equals to 10 times 37,901.6 minus by 110 times 3,400.7 divided by 10 times 1,540 minus by 110 square, more or less, is 1.497. For the intercept, is 3,236.03 divided by 10 equals to 323.607.
We are solving the question asked in the earlier, which is to find 1987 and 2005, and when CO2 level reaches 400%. The year where CO2 levels reach 400 parts per million. So in 1987, y is equal to the slope, which is 1.497 multiplied by 17. And the reason I'm choosing the number 17 is because it is 17 years past 1970, and we'll be starting from 1970 because it is the baseline year. Plus the intercept, which is 323.607, which is more or less 349.05 parts per million. And 2005, the y will be equal to 1.497, which is the slope multiplied by 35, which is because it is 35 years past 1970, plus 323.607, which is the intercept, which is more or less 375.99 parts per million. And now the year when CO2 level reaches 400 parts per million, we'll have to substitute the y with 400, and we'll multiply 1.497 by the year, which is x, plus the 123.607. So we'll take the 323.607 to the other side and minus 400 from 323.607, which is 76.390, equals to 1.497x. We'll take 1.497x to the other side as well, and we'll divide 76.390 with 1.497, which is more or less 51. And now this is a graph to demonstrate all the years alongside the carbon dioxide level in parts per million, which is in 1972, it's 327.3 parts per million. In 1974, it's 330 parts per million. In 1976, it's 332 parts per million. In 1978, it's 335.3 parts per million. In 1980, it's 338.5 parts per million. In 1982, it's 341.0 parts per million. In 1984, it's 344.3 parts per million. In 1986, it's 347.0 parts per million. In 1988, it's 351.3 parts per million. And in 1990, it's 354 parts per million. And the two levels we found earlier, which
So let's move to question 2. Hi, I'm Meng Joe.
Hi, I have question.
So the question for question 2 is a conical tank is being filled with water at a rate of 30 cm cube per second. The radius of the tank at the top is 10 cm and the height is 20 cm. Determine the rate at which the water level is rising when the water is 10 cm deep. So this is the solution for question 2. So it's given the conical tank is being filled with water at a rate of 30 cm cube per second, which is dV by dt equal to 30. By referring to the triangle in the conical tank, tangent theta equals to r by h, and tangent theta will also equal to 10 by 20, and the final result is 1 by 2. So by combining two of them, we will get r by h equal to 1 by 2, and lastly, we need to get r, which is equal to 1 by 2h. So by using the formula for the volume of the conical tank, which is V equals to 1 by 3 pi r squared h, later substitute r equal to 1 by 2h into V, and we will get V equals to 1 by 12 pi h cubed.
Okay. Lastly, divide the volume of conical fluid with time. dV by dt equal d by dt square 1 per 12 pi h cubed. So dV by dt equal pi h cubed per 4 times dh by dt. When h is 10, so dy by dt is 13. Follow the formula. 30 is 35 pi dh by dt. So the final answer is dh by dt equal 0.3x cm per second. Hence, the rate at which the water level is reaching when the water is 10 cm still is 0.3x cm per second. Okay, so this is a formula for question 2. Thank you.
Okay, hi. My name is Haydrian and I'm in FIC.
Hello, my name is Jun Hang and I'm in FIC as well.
Okay, so we're going to do question 3. So the question is, we need to derive the velocity of blood flow from the distance model as given below. The distance model shows that the distance traveled by blood at any time t can indeed be modeled as dt equals 20 plus 5 sin 7.85 t times t. So to explain the model, the mean velocity v0, the term 20 cm per second represent the average velocity of blood flow, whereas pulsation component Bp sin 7.85 t, the term adds a pulsation variation to the velocity, simulating the rhythmic nature of blood flow due to the heartbeat. The amplitude of the variation is 5 cm per second, and angular frequency, it's a W. Yeah, it's a W. W equals 7.85 rad per second. This frequency corresponds to the typical heart rate of about 75 beats per minute. And then the behavior of the model, the distance calculation. So about the distance calculation, the model allowed you to compute the distance traveled by blood at any given time with t and variation of time. As time increases, the distance traveled varies not only with the linear increase due to average velocity, but also with the periodic sine function, which reflects the pulsation nature of blood flow. Okay. Okay, so step one, we need to understand the distance model. The distance traveled by blood at any time t is given in the equation dt equals 20 plus 5 sin 785 t times t. The equation composed of two components, the constant mean velocity of 20 cm per second and pulsation component represented by 5 sin 7.85 t, which varies with time.
So step 2, we need to differentiate the distance function. To find, we need to differentiate the distance function d times t with respect to time t. The velocity v times t is given by v times t equals to d prime times t. Using the product rule for differentiation, where u times t equals to 20 plus 5 sin times 7.85 t, and v times t equals to t, we have v equals to t, we have v times t equals to u times t times v prime times t plus v times t times u prime times t. Here, v prime times t equals to 1, and we need to find u prime times t. U times t equals to 20 plus 5 sine times 7.85 t, while u prime t equals to 5 times 7.85 cos times 7.85 t equals to 39.25 cos times 7.85 t. Now applying the product rule, v times t equals to 20 plus 5 sine times 7.85 t times 1 plus 1 plus t times 39.25 cos times 7.85 t. Now step 3, simplify the velocity expression. Now we can simplify the expression for velocity v times t equals to 20 plus 5 sine times 7.85 t plus 39.25 t cos times 7.85 t. This expression gives us the velocity of blood flow at any time t, incorporating both the mean velocity and the pulsatile variation. So the final answer, the velocity of blood flow at time t is given by v times t equals to 20 plus 5 sine times 7.85 t plus 39.25 t cos times 7.85 t in cm per second.